We start here with the ASF vertex tool and zoom into your area of interest. For this example, I'm going to use an area near Xai-Xai, Mozambique. This is an area that we have done work in before. And you draw an area of interest box under geographic search and Sentinel-1. You do need to add some search filters now, specifically the L1 single look complex and the IW for interferometric wideband. And this will work for any of the other options, so you can leave those blank. Searching will give you all of your options for specific frames and scenes. The selected frame is in red on the map, but it corresponds to a red icon in the list of all of the potential scenes. And what you're looking for is a scene that has an overlap with the area of analysis that you need the most. So once you select one, it will be highlighted in red. You can click on that little copy icon that will pop up when you hover over it. Then you can go over to SBAS search for search type and paste that scene name into the search box that pops up. And there are no specific parameters you need to set at this point. You'll notice from the title it actually says interferometric wideband and single look complex. It gives you a few overlapping areas in red, but it also puts together a network of pairs given the parameters that can be selected using these two sliders. Now the sliders can be moved around to automatically fill in a network. You'll notice there's a warning. That warning is that gaps exist. Those gaps were earlier on. We've had pretty good luck with 150 meter perpendicular baseline, and you can make that duration go a little further, up to 24 days. But you still may have some, I should say, this may introduce some gaps in your network, especially places where there's only one path going through. So you may want to add a couple of pairs. That would be with a custom pair. So you click the plus icon first, and then you connect the two that you wish to connect right there. This is nice because it allows you to add a little redundancy to your network and show a little bit more, or resolve a little bit more of the changes over time. See here, there's a gap. We're going to bypass that. And starting around 2022, you'll notice that the network becomes a little more sparse. That is because of a battery issue with one of the Sentinel-1 satellites that caused it to go offline. So it's only got one satellite going right now. There are plans for replacement Sentinel-1C to go up. Hopefully it will go up soon. Under SBAS filters, you can select a start and an end date. Now, the start and the end date could be the exact days of your analyses. If it is, once you select the start and end date, let's say you go through an entire year and search, you'll note that all of the pairs outside of that time frame are removed. So if you added frames, you may need to select and then click on the minus sign to remove them. This will allow you to narrow your network in. Now, if you've selected days that go right up to the edge of when you want your analysis to begin, you may need to add a couple of additional custom pairs outside of your period of analysis so that you cover you cover the actual time that you need, and you give the network a little bit of a little bit of a starting point and ending point. Or I guess I should say ending point and starting point. So again, we add just a couple of pairs to make sure we completely cover our analysis period. And make sure that we're not cutting off anything prematurely. December 14th to January 13th, we still have not 25 days, but it is pretty close and worth it to fill in those gaps. I'll remove these again because we can further update our time period to be even shorter. And if at any time the time period actually goes beyond what you actually care about, then you don't need to do this process of adding additional pairs. To go back, you just click on the upper left date to go back to the month or year, or you can press the arrows on the right to toggle between adjacent months. This type of analysis is particularly useful in the case of a place like Mozambique when there's a specific dry period. It's useful to download the CSV pairs because that gives you a reference, and it can be used for other download scripts, not the script we're going to be using. And then you go to on-demand InSAR Gamma to add those to your on-demand. You do need to be signed in for that. Then these end up in your on-demand queue, which you can open up, and the 10x2, which is worth more credits, that is your higher resolution option. And the MintPy options button puts in the minimum features, but we've had really good luck with adding all of them. When you do finally submit, and it also shows you the number of credits you have automatically added left, then you can name your submission. And when you finally submit, it will then go into the queue for analysis at the Alaska Satellite Facility. And this is using their supercomputers to create these custom pairs. So you'll see the on-demand queue is empty. The download queue is empty as well. That is because the analysis is not ended yet, and we can check the status at any time by changing the search type to on-demand, selecting the name of the request that you submitted, and then you'll notice that it was under pending. So sometimes I've been surprised that they come back in only a couple hours, but sometimes it takes over a day. When you go back, and as long as you're signed in, you can go back to the same place, on-demand products, select your project name, and if they are ready for download, then it says 1 out of 1, and it gives you a shopping cart option. Or what's more useful is the queue icon here. Now, we've already submitted these, but we do need to make sure that there are at least 40 pairs. That's a requirement for MintPy to actually run. I don't think it'll run at all with fewer than 30, but we would like 40 pairs. Once those have been added to your downloads, you can go to the download queue and then go to data download and download the Python script. This will make the download significantly easier. And I went ahead and cleared it. I would not recommend doing that unless you're very comfortable with the process until after you have confirmed that your download was successful and that you are getting the data you expected. At this point, you can use a terminal window, or you can use the File Explorer or Finder windows to move that download script to the file where you want all of your data to end up. So we put that download file in the directory where we want the data, and then we execute it with Python, or some computers require Python 3 as the command, followed by the download script. You will likely be asked for your username and password. The nice thing is the Python script will restart, or you can restart the Python script if your download is interrupted, either due to space or due to loss of internet connection. I only downloaded a few of these. The commands are available, but you want to use the escape character, the backslash, before the star to make sure that these all unzip all at once. Hopefully you don't have any errors, because if you downloaded them all together. However, we had some errors only because some of the files I had interrupted the download. So I like to use the core.tiff. It's the correlation image, and we're just going to add that to a GIS window and zoom in and take a look at it and just make sure that that is indeed what we want and what we expected. And it is in this case. This is coastal Xai-Xai, Mozambique. And we'll notice that the file is pretty big. So one of the first things we need to do is decide, okay, what is the area we really care about? And we're going to create an area of interest shape file. It does need to be in a shape file. That's the .shp, and there are a couple of associated files, so we do want to make sure to keep with it. We create a new shapefile layer, and that layer type is going to be a polygon. And we can close that. We toggle editing on using the button or right-clicking on the layer and toggle editing. And we add a polygon using the add polygon button, or if we go up to add polygon feature. This allows us to draw the polygon right there onto the map. In this case, it does not actually matter how many vertices you use. And to finish, right-click and click OK. And there we have our polygon. And polygon fits entirely within the image. we can then visualize that a little differently. Oh, and when you go to save it, you just turn off toggle editing and it will prompt you to save your new polygon. So there it is. We selected where to save it when we created the shapefile layer, the new shapefile layer. So that is where it exists. I like to keep it in an adjacent directory called GIS next to the hype data itself. And for the coordinate reference system, for the AOI, that is in longitude and latitude. And for the correlation image, that's actually in UTM. So this is two different coordinate reference systems, and we're going to change that correlation image from UTM to longitude and latitude. And we use that with the warp command. We're only going to do one of them, and we're just going to keep it in a temporary file, or a temporary layer. So there it is, the reprojected layer. And the reason we just do one is because we really just need, you can see a slight adjustment there. We really just need the parameters that we're going to take from it right here. We're just going to confirm that indeed it is in longitude and latitude. And then we're going to take the pixel size. So there's the pixel size. And we're going to copy those two numbers. And those two numbers are going to be used in a bulk reprojection script. So we go over here to the Python script cut_geotiffs.py. And this you can download from GitHub. And we're going to take all of the TIFF files that we found, and we're going to get that using the glob library in GitHub. We're going to crop those down to their area of interest, which we define as clip. And as a final output, we need the lens, the pixel size, the destination pixel size. So we put those in here. Those are the only things that you need to do: the locations of all of your data files, the location of your AOI, and the pixel size. After that, we save this, and we can run it. Again, by typing Python and then cut geotiffs.py. And this is a little different than the one that was available through MintPy. It's the same code, but I changed it to run in parallel, so it runs a lot faster. That is a pretty long duration code. This is the configuration file for MintPy. You just want to make sure that on line 29 it's hype, and then the following lines here, and this is all available on GitHub as well, have the exact locations of your various data files. Cut geotiffs adds that .rprj flag into every single one, so you want all of the .rprj.tiff files. I'm pointing out here the coherence parameters. These are minimum coherence, and you'll notice a lot of these are the number, but it's the number for the default and that is just in case you do need to change it. Now, your reference pixel, that's what MinPy is going to assume is constantly level and not moving up and down. So we highly recommend a GNSS site or a CORS site or something where we can go back and reference somehow, okay, is this pixel moving up and down by some sort of independent area? So the rest of these are all parameters that you may need to change later. Now, the last thing is the PIAPS and the ERA5. Now, we've had some luck experimenting with Mara, and that's fine. PIAPS needs to be installed in the computer separately, and then ERA5, you do need an account with the European Center for Mid-Range Weather Forecasting and accept their license agreement. But that's where you set these or turn them off if you have to. A first run without them is not bad. But this is used for our tropospheric correction, or basically differences in the atmosphere that will change the way that the radar wave propagates back. So those are all of the files you need to prepare for the entire SBAS run. And once all of those are ready, then you can execute them.